Hello. Hi. So we will be starting the morning session in about 2 minutes. So please start finding a seat so we can get started. Okay. Good morning, everyone. Please find a seat. It is my great pleasure and honor to introduce the Posner Lecture. Posner Lecture is an opportunity that we take at NeurIPS to highlight the contribution of someone in our field in machine learning. And the program chairs decided this year to select Joëlle Pinault as our Posner Lecture. So she is associate professor at McGill University in Montreal. She also co-directs the Reasoning and Learning Lab there, and she leads the Facebook AI Research Lab in Montreal. And so Joëlle is known for her many contributions, developing models and algorithms for planning and learning in complex, partially observable domains. She also works at applying these algorithms in various domains like robotics, healthcare, games, conversational agents. And as a student who's grown here in Montreal, I know Joëlle as well as a big inspiration for many of us, seeing her professionally in her career. And also, when I started as a student at NeurIPS, even though it was much smaller then, it was still a pretty intimidating experience. And for me, Joëlle was one of the few people who was generous with her time and approachable, and that definitely helped me feel more welcome in this community. So I think she's the perfect choice for the Posner Lecture. So she serves on the editorial board of JAIR and JMLR. She also is the recipient of NSERC Stacey Memorial Fellowship. By the way, she told me not to read all of these, but that didn't seem appropriate. I think we should all be aware of these distinctions. She's also was nominated as a fellow for AAAI, a senior fellow at CFAR, and she's a member of the College of New Scholars, Artists, and Scientists at the Royal Society of Canada. So it's my honor, and please join me in welcoming Joëlle.
Good morning, everyone. It's a pleasure to be here on this stage, sharing with you some of the things I've been thinking about over the last year. In fact, I've been on a path to try to understand how our community can establish structures, standards, practices to enable us to do better science and to have, in particular, more reliable findings. There's been a call on a similar stage to have more theory embedded in our research. This is not quite the argument I'm going to make today, though I don't disagree with it. But I do think that a lot of science progress has been driven by empirical findings. And so what I want to discuss today is really some of the things that we can do as a community to improve our track record in terms of empirical science, how that fits very practically in some of the work that I've been doing. And while most of what I'll discuss today is about reinforcement learning, I think there's many, many lessons and findings that apply much beyond this and may be beneficial for many people. So let me start by perhaps trying to illustrate what the thread is between the 3 R's that I've picked this morning: reproducibility, reusability, robustness. And as I was thinking through that, in fact, I found this quote from a report, NSF 2015, that seems to say it more eloquently than I could, at least this early in the morning. And so they suggested that reproducibility refers to the ability of a researcher to duplicate the results of a prior study using the same materials as were used by the original investigator. And reproducibility is a minimum necessary condition for a finding to be believable and informative. And so this essentially is going to be our program for this morning, exploring aspects of these properties as they pertain to some of the recent scientific findings in our communities and trying to draw some thoughts on how we should move forward. I'm not the first one to raise this question or concern about reproducibility. It's been discussed in several other spheres and fields. 2016, the journal Nature ran a survey, 1,500 scientists, asking them, is there a reproducibility crisis? 52% of them in dark red said that there was a significant crisis. 38% in pink said there was a slight crisis. About 3% said no crisis here. And another 7% said they didn't know. It's good to show your uncertainty bars, right? Then we tried to tease it apart a little bit more by fields. It may be that the type of empirical work may affect the likelihood that an experiment is difficult to reproduce. On this graph, I'm showing for several fields on dark red whether scientists at some point had a difficulty reproducing someone else's experiment, and in pink, whether they had difficulty reproducing their own experiments. And so the poor chemists are having a really hard time here, right? Over 80% had difficulty reproducing someone else's experiment, 60% reproducing their own experiment. Biology not far behind, physics, engineering, medicine. Computer science doesn't show up on this graph. Perhaps we're folded in with the others, but perhaps they haven't spent the time to think through what may be the phenomenons. And so what I tried to do is figure out what was the incidence of such issues, how did they apply to the work that I was doing, that we were doing in my lab. And so let me set the stage a little bit, because our community has grown so much. A little bit of background on reinforcement learning, where I do most of my work. The idea of reinforcement learning is to enable an intelligent agent to make sequences of decisions. So there's a loop along which the decisions are made. Information is fed into the system through this notion of a state, and the agent has to take actions. These actions are directed towards accumulating reward, and so the objective is to maximize the accumulation of reward over the trajectory or the lifetime of the agent. It's a very general framework for sequential decision making, very elegant mathematically. It also allows the agent to learn to self-train through trial and error. It allows us to consider only very sparse feedback, and also to have an agent that improves over the full lifetime. And so from this very simple, elegant framework, we can actually solve a wide variety of problems. We've had some impressive success from reinforcement learning just in the last couple of years, in particular in solving some very challenging games and showing that RL agents could beat the best humans at some of these games. And while these are very impressive results, in a sense, what has me most excited about this framework is the huge potential for solving real-world problems. And so scanning through the recent literature, we find applications of reinforcement learning ranging for things like robotics, video games, medical intervention system, managing agricultural crops, prosthetic arm control, financial trading, and so on and so forth. And so you can imagine that there's a huge number of people that are looking very closely at this framework and are looking to use the results coming out of the scientific community, who are pushing the edge in terms of algorithms and models, and trying to imagine what is the potential of these methods for solving important problems. In some of my own work over the last few years, we've considered the problem of optimizing the parameters of a neurostimulation device, a small device implanted that allows stimulation of the brain to prevent seizures in individuals with epilepsy. In the case of this device, we actually have an electrode doing EEG reading in real time of the human brain. Most of these experiments were actually done in animals, I assure you, at this stage. And you will understand why when you see the rest of my talk. And so we're doing neurostimulation, we're looking at the EEG signal, we're pulling out features of that, and we're training a policy, a strategy that decides when to do the stimulation in a way to minimize the incidence of seizure and ideally also minimize the amount of stimulation that's deployed. You can imagine that in an application like this, having sound empirical result matters a lot. You can also imagine that in an experiment like this, I can't afford to gather the millions of trajectories that were used to train the system that are used for games. And so one of our challenges as we go outside of the realm of games and simulators is to figure out which methods are reliable and which will transfer from the simulation domain to the real world, where we can only afford a handful of trials, maybe a few hundred or a few thousand if we're really lucky. This is really the crux of the reason why I'm so interested in reproducibility and robustness. And in many of these cases, if we manage to do that, not only can we have better neurostimulation devices, we can also have better artificial pancreas for people with diabetes. We can have better methods for discovering and treating patients with cancer. And so when I engage on some of these projects, of course, I voraciously read the literature and look at everything that's happening. What are the recent trends in machine learning? What are the recent trends, particularly in reinforcement learning? And where can I draw inspiration to solve these important problems? So this is a quick graph of the number of papers in reinforcement learning for 25 years or so. I started working in reinforcement learning and looking at applications in robotics around 2000. So that's a point right around here, right? It's about slightly under 2,000 papers published at that time. And what matters here is not really the number of papers in a given year, it's really the area under the curve. Turning quickly to 2018, over 20,000 papers published this year in reinforcement learning. And the year isn't over yet. Many exciting ones appearing this year. But it makes it a challenge not only to keep up with the literature, but also to tease apart within this huge volume, what are the few gems that really hold promise to solve important problems. And so for the rest of the next 15 minutes or so, I'm going to focus on one particular class of reinforcement learning that have gotten the most attention possibly and show a lot of promise for practical applications, and that is the class of policy gradient methods. So in policy gradient, really the idea is that you learn the policy, the strategy, as a function. And this function can be represented these days by a neural network, though in years past it was by other regression functions. Into the neural network comes the state. Out of the neural networks comes an action. In the case of continuous system, you may have one variable for each dimension of the system you're trying to control. In the case of discrete actions, you may have the probability of each of the discrete actions coming out. And that neural network essentially contains your policy. It's parameterized by a set of parameters that I'm denoting by theta over here. And the goal is to maximize the return as defined by the sequence of reward condition on the initial state. And we do this using standard gradient descent methods. We want to maximize the reward. We consider the distribution over state that's induced by the policy, right? If you use a different policy, you're going to see different states. And so we consider the expectation with respect to the states we see. We look at the gradient of the policy with respect to the parameters, and then we look at the empirical return either through a Monte Carlo or another fitted function. So if we look at the space of policy gradient papers appearing, that's a long list also. Not quite 20,000, but a pretty long list too. I've pulled out some titles of papers that are going to be presented this week at NeurIPS. Apologies if I missed yours. There are more than those ones just shown here. And there's also a long list of them that appealed in other top conferences, ICLEAR, ICML, AAAI, WRL, CoRL, lots of papers. As someone who reads that literature, I have to figure out among all of these, which is, of course, the most promising, but they don't compare to each other because they're all appearing so quickly. So in many cases, my best bet is comparing how well they do with respect to the baseline algorithms. Most of them in their work include empirical results and also include comparison to some baseline. And it turns out, though the volume of papers appearing is quite large, the number of baseline methods that they consider is much smaller. And so there's 4. I've picked out 4 for today. They're not the only ones, but they're probably the ones that come through the literature most often. TRPO, PPO, DDPG, ACTOR, all relatively recent, last 3 or 4 years or so, but really used in many, many papers, high citation rates. And we started playing with these algorithms in our lab, trying to compare them and trying to see what are the trends in simulation to compare one versus the other, hoping to distill knowledge that we can then apply to our real-world problem. And so we started with the Mujoko simulator, a common benchmark environment where we control these animated characters which have a few joints, and we compared the 4 algorithms. And for the purposes of today's talk, actually, I'm not going to tell you which algorithm is which. Really, the message is about how do we go about this kind of empirical comparison. So based on this simple experiment, it seems to be that the red algorithm is doing significantly better than the blue, somewhat better than the orange, but perhaps has a little bit more variance than some of the other methods. This is sort of what I would read out of that graph. So that seemed a piece of evidence, but since simulation is cheap, we can afford to run a few more domains. So we ran similar domains, the hopper, the swimmer, which are variants on these animated characters, with the same set of 4 algorithms. And then the results were different. All of a sudden, the blue algorithm seemed a lot better. On the hopper environment, the blue has very small variance, but then on the swimmer environment, the blue has really large variance. Not completely surprising. These are different domains, but they're all the same kind of dynamics on the same physics emulator, running on the same computer. And so if I can't even hope to have reliable comparison between these on this simple class of algorithms, it makes it a little bit challenging for me to know what to do when I want to do neurostimulation. And so at this stage, we had a lot of heated discussion with the team, and we thought maybe we don't, we didn't implement these on our own. We thought maybe we didn't pick the right code base. So we went back, and it turns out that conveniently enough, several people, including possibly some of you in the audience today, generously provided code, and I'm a strong supporter of open source code. And so we tried a few other packages, all for TRPO. And again, we got pretty surprising results. Blue, red, yellow, all TRPO, 3 different implementations. It's not just TRPO. We tried the same thing with DDPG, grabbed a bunch of open source code, and again, significantly different. Now, on the half cheetah, the blue code seemed to be doing really well, and on the, the half cheetah with DDPG, the red seemed to be doing very well, but it's not really clear where to go from there. And so we started digging in a little bit more. Most of the time we started, as many of you do in your papers, with the default set of hyperparameters for the models. So we started playing around with the network structure, right? Remember, I have a neural network for my policy, changing the architecture, looking at different types of unit activations. Again, huge variance in results. We started playing with reward scale, whether we were using layer-wise normalization. Huge set of different results. And at this point, we were actually quite motivated to find the best configuration, but the worry we had was that perhaps people writing papers were not always as motivated to find the best hyperparameters for the baseline, and perhaps very conveniently often use the default hyperparameters. And so, in one sense, this is a little bit of a plea that if we are doing comparisons as a community, whether it's for a baseline algorithm or for your new fantastic idea, to really think carefully about using the same amount of data and the same amount of computation when comparing methods. That seems relatively simple, so I hope there will not be much controversy about this one. This is something we tried to apply in our own group, and so after much discussion, we decided to redo some experiments, normalizing in particular the hyperparameter budget happening between different methods, go back to some experiment, and we ran another one. And a week later, my collaborators came back and said, Joelle, we have a really interesting graph for you. Here's this one. 2 different runs, averaged over 5 different ones, each of them. It seems to be pretty clean that orange is doing better than blue. I asked, did you spend the same amount of data, the same amount of computation? Yes, yes, we compared these 2 very fairly. Then I asked them, okay, what are these 2? It turns out both of them were the same TRPO code with the best hyperparameter configuration that could be found. Just 5 different random seeds on each of them. That's a little bit problematic. So we thought, well, you know, maybe it was a particularly funny run. Clearly, N was not large enough. We need to run most of this, and it should somehow, you know, get a little tighter. So we tried to do that. And I asked them, you know, why did you run 5 runs? Why did you think that was enough? Clearly, you know, picking out that factor N really influences the size of our confidence interval. So how should we be picking N? And so my collaborators said, well, you know, we looked at the literature, saw how many trials people were doing, and 5 seemed to be like on the upper side of things. So we thought we were doing well with 5 trials. These are some of the recent papers on reinforcement learning, not quite 2018. And it's not necessary to identify the authors because I promise you they're not the only ones doing this. And this is the thing about reproducibility, right? When enough people start doing something, then the next generation of people think that's the thing to do. We were taught to read the literature and follow the methodology and replicate what's in the paper. And so not only were people running only 5 runs, some people were doing this thing. When I heard about this, I thought it was marvelous. They would run N runs, N was not specified, and then they would report the top 5 results. I thought this was fabulous because that's a really good way to get good results. Let me be very clear about what happens when you do that. This is what happens when you run 10 runs of some algorithm that has a little bit of maybe random noise in the rewards and this transition probability, and assume you've got some baseline to beat, and this is your algorithm that you're very motivated to show does well, so you can write this beautiful NeurIPS paper. If you pick the top 3 results, 1, there's a very strong positive bias, so it becomes much more clear, easy to beat the baseline. 2, the variance appears a lot smaller, in particular when you're doing this max operator in there. And this is something we should know in reinforcement learning. So I've been talking about these results here and there in workshops over the last year, and you know, the message sort of at some point got a little muddled. Some people use this to argue that the whole field was broken, and quite frankly, every lab and university should just fire all of its reinforcement learning researchers, and we should just not use this kind of technique. And that is not my message for today. I hope this is recorded. This is not my message for today. Right? My message is that sometimes fair comparisons don't tell the whole story. And just because you give an equal amount of data budget and computation budget to 2 algorithms, it doesn't mean that you get the most knowledge out of your empirical study. First of all, different methods may have a very distinct set of hyperparameters. In some cases, if you're considering random forest versus neural networks, the number of hyperparameters is very different, so it's normal that you may need a different budget to properly optimize the hyperparameter. Different methods have different variable sensitivity to those hyperparameters. That should be taken into account. And most important, what method is best often depends on what is your data budget and what is your computation budget. And so this is something that I hope everyone takes into account. This is a lot more subtle than just telling you to use the same computation budget and use the same data budget. This requires careful thinking about your experiment, and most importantly, it requires very careful reporting about your experiment. And so since I've been talking about this, the first time I talked about at least some of these results was in the DeepRL workshop a year ago, and since then we've really evolved some of our thinking about it. We went back in the last 3 weeks and looked at papers, this time only papers from 2018 that were published at NeurIPS, ICML, iClear. We took a sample of 50 papers. There's a lot more than that, but we looked at 50 papers. All of the papers we considered had experiments, so that's good. That seems relevant for our discussion this morning. 90% of them used the very fashionable neural networks. 90% of them described all the hyperparameters needed to reproduce their own methods. So that was reasonably good. Hyperparameters for the baseline were reported in 60% of papers. That makes it a little bit harder for us. Code was linked in 55% of the cases. Better than I had expected, I must say, so the trend is definitely in the right direction. The method for choosing the hyperparameters, right? How did you optimize? What was your budget? 20% of papers. Some evaluation on a holdout test set, 10% of papers. And significance testing applied, 5% of papers. Presumably significant testing is the one thing we care about. So there was a lot of graphs that had figures that looks like this, right? Shading looks good, of course. The challenge is when you don't tell us what your shading area is. And you would be surprised about the number of papers that don't tell you whether you're looking at a 95% confidence interval, a 68% confidence interval, a standard deviation. Shading looks good, but shading is not knowledge unless you define it properly. So, to make it a little easier for you for 2019 papers, in consultation with colleagues, we have come together with a reproducibility checklist. The first part will seem relatively straightforward. If you present an algorithm, you should include a clear description of your algorithm and analysis of the complexity. And you should think about including source code, and it's on your conscience whether you check that box or not. If you make theoretical claims, you should have a statement of the result, a clear explanation of any assumption, and a complete proof of the claim. Should you wish to include figures, tables, results, then you should think about having a description of the data collection process, a link to a downloadable version, some explanation of how samples were allocated, training, validation, testing, an explanation of any data that was excluded. So if you're taking the top 5, you got to explain to me why the other K were not kept. The hyperparameters selected, how you selected them, so on, the number of evaluation runs, a description of the specific statistics, error bars, I love error bars, both the central tendency, the mean is great, but also some measure of variation. And I don't really care if you give me a 95% confidence interval or some quartile interpretation, tell me what it is. And finally, the computing infrastructure that you used. Let me say, I will make this available for anyone who wishes to use it. Anyone who's a program chair in 2019, I encourage you to include this checklist as part of your submission process. On the role of infrastructure, right? We often feel that because we're running things on computers, things should be relatively predictable, at least much more so than in the other sciences. Remember the poor chemists? Yet it's been well documented that, at least in clinical science, often just the identifier for the center where the care was given is one of the best predictors in terms of outcomes measured. And so I think we still have to be a little bit cognizant of the fact that depending on how we're running our experiments, there may be a little bit of variability, especially as we use distributed training system, depending on how the scheduler is used, what are some of the properties of your CUDA operations, and so on. So there's room for a little bit of variability, even in hardware, and that's why I think specifying it can be useful. Now that we have a checklist, we should feel much better prepared for the next year of science. And so I want to spend a little bit of time on another statement that has appeared in the last year, perhaps quite controversially. Since we didn't yet fire all the RL researchers, we must respond to this accusation. Reinforcement learning is the only case of machine learning where it is acceptable to test on your training set. What's the deal here? So, in classical ARL, indeed, it has been the custom to train on a particular task, be it a maze, a particular maze, or a game, a particular game, to train our agent to accomplish that one task, and then at test time to run the optimal policy or the learned policy on that same environment. And I would say on the roadmap to AGI, this is a starting point. And where we want to be is really have the ability for AI agent to test on anything. Right? This is essentially AGI. The world is your test set. And while we've done a lot of good work at the left side of that, I'm here to encourage you to explore the full spectrum of opportunities that stand between the classical RL paradigm and AGI. And so one of the things that people have done is actually to use separate tasks for training and for testing. So I'm going to run my RL agent on a class of mazes or a class of games, and then I'm going to test on a different classes of maze and games. And while I think that's a good way to test generalization, that's not quite the space I'm going to explore today. There's a lot of work on multitask and meta-learning and so on that explore that piece. I want to explore things that don't quite go that far as requiring completely different tasks with different goals. Something that's maybe a little bit closer, but still allows much more variability between training and testing. And so the following ideas was proposed, and this is one we've explored this year, is to actually have simply separate random seeds for the training runs and for your test run. And so this isn't that complicated to do, assuming there's enough variance in the task, variability in your initial state, in your stochastic reward, your transition, this should make a difference, right? And so we defined a nice, simple generalization error. On the one hand, you're going to look at your empirical return with the states that you visit in your training seeds. And in another case, you're going to have the empirical reward you see in the state that you see with your test seed. And as you learn more and more, hopefully the performance will reduce. And we tried that on a very simple task, this Acrobat simulator. And we looked what happens if in your training seeds, you just have one training seed. So you can have as many training trajectory as you want, but you're only allowed to observe like one starting position. And then there was a big gap, right? The line in green up here, that's my generalization error. So that's a big gap between what I think I'm going to get when I train and what I actually get when I test. So then we move to 2 seeds and 5 seeds. And as soon as we get to 5 or 10 seeds, essentially my generalization error completely disappear, right? So in a sense, that's good, right? We want low generalization error. That's really good. It's a little bit worrisome that so few seeds allow you to essentially memorize the domain. And when I asked some of my robotics colleagues, who I know have been working with a very similar setup in their work, right? They trained a robot to do this. I asked them, 2, 5 initial positions, surely that was enough for your robot, right? It turns out not. It turns out the real world is not quite so predictable. In fact, has a lot more variability than our simulators. In fact, the real world has incredible complexity. And when we go to these simulators, that complexity is completely lost. Standard robotic sensors, like a Bumblebee camera, is going to have like maybe 10 millibytes of data coming in every second. The natural world needs on the order of zettabytes to be described. And yet we're running with RL benchmark that have a simplicity. The Mujoko domain's very low state space. ALE has a lot of different games, but very small number of actions. Both cases, mostly deterministic transitions reward. If you actually look at the code to write some of these, right, the code is on the order of like 100 kilobytes. You can essentially describe the whole world with 100 kilobytes. Compared to the natural world, this is ages apart. And so as we move on the spectrum of generalization, one of the things we have to do is really break out of these simulators and find a way to tackle RL in the natural world. Now, I realize it's a little bit difficult for all of the RL researchers to have access to labs to do neurostimulation and robots to run experiments. And one thing I love about the simulators is the fact that they help reproducibility. I can run my algorithms on something, you can do the same, we can compare a result in a very fluid way. So we wanted to find a mechanism to keep the convenience of the simulator, but do it in a way that we can actually include some of the complexity of the real world. So we started brainstorming about this, and the first thing we came up with is this cute little task where we take an image and we turn it into an RL simulation. So take an image, any image, and the goal of the agent is going to be to run around the world, and as it runs around, it acquires more and more information about the image. So the state is the image at any time and point. The RL actions are to move in the 4 cardinal directions, and at some point, the agent has to declare victory. It has found this is a lantana camera, and if it gets the right guess, it gets the reward. And so very convenient, because these images are taken from the real world. They have the natural noise that I'm seeking. They embed it into an RL system, and they do so in a way that I can share. All I have to do is send an image to someone, and we can run on the same RL domain. A little bit simplistic in terms of dynamics and actions, but at least on the observation side, I have wonderful variability. And when I do this on the CIFAR 10 data set, where I have a lot of images, and I use the standard train test split, so all of the training images can be used as simulation environments for training. All of the testing images are used for testing. Now, if I look at my generalization gap, I see that to get my generalization error all the way down, I need on the order of 10,000 training seeds. And so that's a lot more healthy in terms of variability, I think. We did this not only for CIFAR 10, we also did it for MNIST, we did it for CIFAR 100. And what you also start to see if you train different RL agents, in the 3 graph below, I have 3 different RL agents that we've trained, you start to see nice separation. In the very easy MNIST task, the blue and the green algorithm are actually neck and neck for performance. As you move to CIFAR 10, green really starts to pull ahead. As you move to CIFAR 100, green has a nice big separation. And so there seems to be also some discriminating power in terms of comparing algorithms for this task despite the simple dynamics. Static images are nice, but they don't require a lot of strategy. And you could probably make the argument that with a good, information gathering heuristic, you could get a policy that doesn't need, PPO or something like that to be trained. And so we started looking at a second strategy for doing this. In this case, we looked at the Atari domains, realized that many of them had a very simple background, black background. In this case, a game called Breakout, right? You control the little palette at the bottom. If you hit the ball and it touches a brick, you get some points. And we thought, what if we could make this a lot more interesting with natural world signal? And so we spent some time taking Atari games, and instead of a black background, we pipe in some video. Videos from the real world. Video's an endless source of natural noise. And the beautiful thing about video is I can use some videos for training, I can use some videos for testing, and if I want a completely new test set next year, I just grab some new videos. And in doing so, as long as I have a process for grabbing videos, I can have a simulator that I can share, that we can all use. We can have as much data as we want. The strategy aspects are still respected. In this case, we asked a human. We haven't yet trained the RL agent for this. I invite you all to try it out. We asked a human to play the game, and we show that though the game is a little bit harder for the human, they can still play. There's a little bit of distraction from the background, but it's still a doable game. And we have easy replication and comparison. In this move from static images to video background, I think there's a lot further we can go as a community. One of the things that has been investigated by some of my colleagues at Facebook is actually the creation of simulation environments that are completely photorealistic but have full properties of simulators. So in this case, the simulator is essentially an emulator built from images, videos that were taken from real homes, thousands of real homes. You can have nice separation again with training and testing. You can actually set tasks like get the ball, find my keys. If you look at this one, there's particularly nice effects through the mirrors, which some of the colleagues at Facebook Reality Labs have been working on. And it gives you a really high variability of different domains. So going back to this, do we really have to train and test on the same task? I would argue that we really don't. At a minimum, we can start by using different random seeds. It turns out that not a lot of seeds are necessary with our current simulation environment. There's a lot we can do to incorporate natural noise in the environment, whether through image, through video, and eventually through photorealistic simulators. I encourage you to explore that full spectrum. I think simulation and the ability to share environment is great, but I think really we can set the bar much higher in terms of the realism of our simulators. And should you, once in a while, want to tackle a real-world problem, I do encourage all of you on a regular basis to step out into the real world and tackle a real problem. One where you might not control how data is acquired. We worry a lot about exploration policy and solving the exploration problem. In my experience solving real-world problem, I never got into the project early enough, or rarely did I get in the project early enough that I can control exploration. Most of the time I'm given data collected by some strategy. If I'm lucky, there's a little bit of randomization in that strategy, and I'm given the task of learning the best policy I can and then testing that policy. When we did the neurostimulation project, we got the data, not controlling the strategy. It had been collected with a fixed stimulation policy. We spent 6 months, 8 months learning the best policy we could. At some point we were ready. We had this pi star, our optimal policy. We went back into the lab and we were not allowed any online learning. We deployed the strategy. It took 2 years to just do the policy evaluation, get enough animals so that we could get significant results in terms of showing that the optimal policy was better than the current standard in the literature. So you have to be patient if you want to do real world, but in doing so we learned a ton about what were realistic assumptions, what kind of methods worked under these conditions, and it has inspired since then a lot of our more recent work. So I've been given this really amazing opportunity to speak to you this morning. It's really been an honor, but I do come with you with a few messages. The first one is really to let go of this notion that science is a competitive sport. Science is a collaborative process. It's a collective institution, and it's through sharing of our results and sharing of our methods that we are going to do better science and that we are going to have a better ability to understand and have a positive impact on our world. In some cases, consider using our checklist. We will make it available for anyone who wants to. The checklist isn't really meant as a safeguard towards letting papers in. It's really meant as a reminder to each of us of what we should be looking for in terms of good science in our own work and in the work of others when we do reviewing. Should you feel like you want to contribute to this work, this effort towards reproducibility and better science, we have launched the iClear Reproducibility Challenge. We are now in the 2nd year of the challenge. It's still not too late. The goal is to get members of the community to take on the task of reproducing the empirical results in one of the iClear submissions. The use of open review makes it very easy to have access to the work early on, but also to communicate back to the authors the results of your findings. When we did this challenge last year, after the fact, we asked authors who had received reproducibility reports whether they appreciated it, how many of them changed their paper as a result of that feedback. 80% of them said they changed their paper as a result of that feedback. We also asked them, would you want your paper to enter the reproducibility challenge next year? 80% of them said yes. Right now we have 31 institutions participating, about 100 papers are being replicated, but there's many, many more submissions at iClear, and we have a mechanism through GitHub to ensure that you're claiming a paper that hasn't been reproduced by another team. So if after NeurIPS you have nothing else to do, and you need a break from your own science and you want to help someone else's science and the community, please jump in, do your share. If you feel like after today you either don't know anything about reinforcement learning or want to learn a little bit more, I'm delighted to say we have a monograph appearing this month at Foundations and Trends in Machine Learning. I encourage you to read it. And it contains a chapter with some of the reproducibility results I discussed today, though not all. As I finish, let me take the time to thank my fantastic contributors. I'm going to name them: Peter Henderson, Ria Shatislam, Josh Ramoff, David Meager, Doina Prekup, Phil Bachman, all contributed to the RL reproducibility work. Amy Zhang, Nicola Balas, and Yuqin Wu contributed to the work on natural RL. And I continue to be supported and inspired by my labs, both at McGill and at FAIR. Thank you very much.
Yeah, so, I mean, I'm a theoretician, and I'm listening to it with some kind of puzzlement, because for me, trust in results comes from proofs, from mathematical proofs. And you hardly ever mentioned it. I mean, it's like we are in the early ages where all we can do is probe around for experiments. What about more, provable guarantees or provable limitations for RL?
I'm all in favor of proofs, and I mentioned it maybe too briefly in the beginning. I think the case can be made that we need much stronger results on the theoretical side. The reality is, in many fields of science, including reinforcement learning, there's a lag between what theory says and what empirical results say. And so this is not in any way a claim that we should only do empirical work. This is simply a call that for anyone who does do empirical work, and I think empirical work is important, to do it well. And then I'll leave it to others to tell us how to do the theoretical work well on a different day. But absolutely, I strongly support good theory.
Thank you for a great talk. Just wondering whether you can comment on the fact that, unlike a more artificial simulation environment, in a more of a natural type of input data, it might be a little bit more difficult to actually characterize those data. So I'm just wondering whether you have some comments on regarding the kind of embedded bias, things like that. Thank you.
So just to clarify, you're asking whether it may be more difficult to characterize natural data when we pipe it in.
That's right.
And the properties of that data and the distributions and
exactly,
so on.
Exactly.
Yeah, I think that's absolutely right. Definitely. I showed this where we feed in this video in the background, and it's possible that there's a lot of variability in the types of videos that get fed in. In a sense, when we do pure simulation, we can control that a lot, and in the examples I showed, we don't control that at all. And I think the level of control that we impose on that has to do with how we sample the natural world. And so in some of the works where I just sample images, we're looking at one modality in a certain number of pixels of the natural world. And so that allows us to generalize within that space. What I like about these ideas is it's really more a way of thinking. I'm not being prescriptive completely about how you should simulate the world. I'm calling on everyone to think of creative mechanisms to feed in natural world. So if you have a method that you think is more adequate for relatively controlled variability, there's a way to sample the natural world for that. And if you really want to go all out, then we're hoping to have some nice 3D simulation environments built over the next few years.
Hi, Joel. Nice talk. One quick remark and then a question. With RL, there's more than the machine learning component, right, and generalization. There's also the planning component. And I think if you take that perspective, some of the current practices are not that bad. But this is probably requires a longer answer. How do you square the idea of using a reproducibility checklist with the current conference culture that we have, with the really short review cycle, and just to be blunt, the superficial review cycle that we currently have? I think what you said on the ICLR side of things is a step in the right direction, but do you have anything more to say as how we can change as a community to reflect those standards?
Yeah, I think in terms of, you make a very good point that RL is both the learning and the planning. And one of the things, I'll be candid, that I'm really not satisfied with is our ability to have natural noise in terms of our control and our plans, right? The effects of the actions and so on are still very deterministic. So if anyone has ideas. In terms of our ability to incorporate new practices with respect to publishing and submission and reviewing, I'm quite hopeful that we can do that. I think I've been pushing a lot in the last year to have mandatory code submission, mandatory data set inclusion in the papers, and I've had some really good discussions with folks. And in a sense, the checklist may be a little bit backing away from that, in that I'm not requiring anything, I'm just requiring accountability. So I'm asking the authors to do an audit, a careful audit of what they're putting in their paper and answer this honestly. And then so I'm suggesting we use these kinds of checklists at submission times, the author fill them, but then the reviewers can actually check whether what they saw in the paper matches what's on there. And eventually, I should have said, I'm sorry, I apologize, I didn't say it, but this checklist was actually inspired by a checklist that's been introduced in the journal Nature. It looks very different because they're worried about different questions and different equipments and different methods, but the spirit is coming from there. And in their case, they make the checklist public at publication time so that people who read a paper know what's in there and know what they're in for. They'll know if there's code and data set and so on. And so having that accountability is what I'm trying to encourage here.
Yeah, but I do think we have to give reviewers the space and so on. That's a pretty significant set of standards that, if we want to enforce them as a community, we've got to maybe rethink a little bit how we do reviewing.
Absolutely. Thank you.
Thank you for the fantastic talk. I love the idea of the video Atari benchmark. I was wondering, in your experience in pushing towards real-world RL problems, where do you see the key challenges that we need to address? So is it in the complexity of the observations? Is it the complexity of the dynamics? Is it the reward structure? I'd be really curious to hear your thoughts on that.
So I think with the natural signal, the type of natural signal we've put in, we really touch on the nerve of like the complexity of the observation space. And in a sense, that's an easier one to tackle because we've had fantastic progress on deep learning that enables us to deal with that. It's still really hard in RL to handle, the very long planning sequences with the very sparse rewards, and this doesn't really tackle that yet. And so I think we're in the next year, we're going to be looking for ideas of how to do that, but in a mode that still preserves the ability to get lots of data and to share environments and to reproduce results.
Good morning. Thank you for the great talk. So listening to your talk and listening to a previous talk on Monday morning on adversarially robust machine learning, I see this community grappling with a lot of problems and finding solutions that a different community has already grappled with and solved to some extent, and that's the community I come from, the control theory community. So I'm wondering if you have thoughts on the way to bring these two communities together for what I think would be good for all, basically.
Mm-hmm. Especially on the aspect of robustness, I think the control community has done a lot. There's some members of the RL community that do have a foot in each and help us bridge some of these ideas. I would say there's a conference, RLDM, Reinforcement Learning and Decision Making Conference, that really tries to take RL from a much broader perspective and welcomes people from control, from neuroscience, from economics, and so on, and get together. And so that's one forum we have for exploring the much wider set of ideas and trying to build bridges.
Thank you for this great talk. My question is, as a supervisor, how do you guarantee that your students replicated an algorithm correctly before putting it in a baseline? Just as a simple example, recently in CVPR there was a publication that went out and the whole testing procedure was flawed in the code, and it was discovered later and called out on Reddit basically. So that was not discovered during the supervisor review process, not discovered during the CVPR review process. No. How can this problem be remedied in relation to reinforcement learning, for example, where it's much more difficult than standard machine learning to quantify stuff?
I think there's no perfect solution there, right? It's about making very clear to the students on a daily basis that good science is better than just pumping out the papers. And understanding, really, we're always after understanding what is going on. This particular work came out of my students trying to implement baselines and being quite frustrated by the results. One thing that's also important to keep in mind is, ask a lot of questions and question the good results as much as the bad results. Sometimes the result seems a little too good. Really question how the method was done. Why suddenly did we get a X% improvement? What was it? And make sure we understand what's going on. And in some cases, pair students up together and ask them to work together.
Thank you.
Thank you for the great talk. I think it's very useful that you aspire to our conscience as scientists, that you remind us that evidence is important, good quality evidence. But I'm afraid this might be fundamentally about incentives. People actually are not very strongly incentivized to, make their baselines look strong in the papers. How can you use your great checklist, in this science as this institution project to actually reward good research?
It depends a little bit on the context, right? I think sometimes like a healthy amount of competition can be helpful, right? Asking different people to implement the baseline versus a particular algorithm can be one way to kind of try things out. Asking a second person to replicate in the lab some of the results can be another good way. And then being very careful about documenting what space, it's a lot in the space of hyperparameters that is search that a lot of the competitive advantage comes. And so being diligent about making sure that you have appropriate confidence that each of the methods were sufficiently explored.
Thanks.
Compliments for the talk. It was very interesting. I have a question. For sure, as you say, it's fundamental to document all you did during your your experimental research, okay? But for what it concerns significance testing, wouldn't that actually make the problem worse? Because in statistics, a lot of people are arguing for moving away from null hypothesis significance testing. And especially in the case of reinforcement learning, where you can decide which data to exclude, how many runs to report, which parameters to move. If you don't make a pre-registration of your study before, then that p-value that you will get can be basically anything, and it's very difficult to compare it. So it makes things, in my opinion, more complicated, not simpler.
Yeah, I think this is an excellent point, and in a sense, everything you say and everything we've heard about this applies in this case also. There's no magic bullet. I think, documentation and accountability is no replacement for good science and good methodology. I think we don't have anything new to suggest to address some of the challenges in terms of significance testing. I think we're really aware of what's going on and looking to other communities to see if there's better ways to do this. But at this stage, really, I'm calling for more thorough documentation and accountability. But it's good to remember that it's not a solution in itself to some of the challenges.
Thank you.
All right, this will need to be our last question, but I'm sure Joelle will be happy to answer questions offline. So let's thank her again. All right, and then we have a break, and then the various sessions of the different tracks will be starting in a few minutes.